So yeah, we're going to start next section here. Last time we did Bernoulli equations, and actually we're going to do the same section, but another kind here. It's called homogeneous equations. Okay, we'll do those a little bit. So this is section 2.4 continued here, I guess. So these are called homogeneous, nonlinear ODEs. Okay, now we talked about homogeneous before. Okay, well, actually, let me write this down here. I'll write a little definition. So a nonlinear, okay, ODE is called homogeneous I'll just write here. If it, I'll just write. Oops. Okay, so if it can be written like this here, okay. So if you have dy dx equals, and then this right side, it can be written. You have a function over here, but it can be written as like a function of just y over x, okay, like this here, like a ratio of y to x, like that. Okay. Yeah. So let's just go to an example. Okay. Now, in that case, if it's a homogeneous equation like this, basically just do this then. You look for solutions of the form y equals ux, like that. So a lot of these problems we're doing here, it's just look for solutions of the form, right? So different equations, you look for solutions of different forms. Okay, so for this type here, we'll look for solutions of the form y equals ux, like this. Okay, so let's just try it out an example here. It's actually not too bad here, but so example here, let's say we have dy dx equals y cubed plus x squared y over x cubed, like this. Okay, so we're trying to figure out here. Look for solutions for this one here then. Okay. Now, first thing here with this, we're trying to use this idea here. Is there a way we can take this right side and write it as a ratio of y over x? Okay. Well, if you look at this kind of carefully here, right, you can write it like this. Dy dx equals, if I divide up and down by x cubed everywhere, okay, like by x cubed, divide by x cubed, divide by x cubed, okay, then it reads like this, right? You can say that's like y cubed over x cubed plus, and then this would be like y over x over 1, basically like this. If you divide up now by x cubed everywhere, right? So this one by x cubed, and this one by x cubed, and this one by x cubed, right? It reduces down to this. Okay, so then you get dy dx equals, and then you can write that as y over x by exponent rules, right? Like this. Basically like this here then. Okay, so for this particular equation, this is a homogeneous differential equation. Okay, because you can write the right side like this here. So, okay, anything so far? Now, okay, now once you know it's homogeneous, okay, then now this guy up here, then you look at this, right? Y equals ux, like that. If I divide both sides by x there now, okay, it reads like this. Basically, you just get that dy dx. Well, okay. Yeah, it's homogeneous, right? So you can write like this. So you get dy dx. You say this is like well, okay. once you have like this here, you look for solutions like this form right here, right? So what you do, you just plug in the y here now. And even easier than this, actually, let's write this much here, right? So it's like this now. You got dy dx equals u cubed plus u, right? You can write this here then, okay? Because you can divide this across here, like the x, like this here, okay? But then if you substitute in here, basically, you can put the y equals ux over here for the u, or I'm sorry, y equals ux in place of here the y then, okay? You know what? I'm actually going to back up on something here real quick. Let me back up here. I'm going to show you something else here with this. So once you have like this here, okay, then you can just look for solutions like this and plug it in. Okay, so, or another way to tell it's homogeneous too, I'm going to back up a little further here. It's homogeneous, right? Because you can write it like this. You can actually tell from here that it's homogeneous. Okay, and what you could do, basically, if you look at the powers here, okay, how do I want to say this here? This is like a y to the third, right? Y to the third. If I look at this here, I add up the exponents here on this term. It's like the third. You have x's and y's, but if you look collectively there, right, you have a third power here. This is basically a third degree here. Okay, and this is third degree down here. If all those degrees are the same, okay, it's going to be homogeneous. Right? Does that make sense? Right? So if this is like a third degree here, this is like a third degree here, this is a third degree here. So if you have like if the numerator is third degree, and denominator is third degree, okay, you're always going to be able to write it like this. You're going to divide it out like that. You can always write it as just like a ratio of y over x here. So once you recognize that, okay, you can even tell from right here, just do the substitution. I would just do it right here, actually. So once you see everything's third degree here, it's all the same, okay, just go for this right away, okay, so substitute in. So if I call this number 1 up here, I'll say subbing into 1. Okay, so it's homogeneous. You can tell from this. So what happens there then? So I get, let me say subbing y equals ux, like this. Y into number 1 here. What happens there? And so you get d. So you take the derivative here then. Okay, so you got to use the product rule there, right? So it's u prime x plus u times 1. So I'm subbing y equals ux into this now. Okay, equals, so that's just from the product rule on the left, subbing in here. Okay, then over here, if I sub in, what's that? I get, that's y cubed, so that is ux cubed plus, and then I get what there? I get x squared, and then y is ux. I'm subbing back into this one here, into the first one, over x cubed, like that. Okay, so you get what? U prime x plus u is equal to. Now, look at what happens here then, right? If you do your exponent rules here, then you see what happens. The x cubes are going to go away, right? Because if I do, let me just write this. I have u cubed x cubed plus x cubed u over x cubed. Okay, like that.
I like how you originally did it when you manipulated.
You like it like this better?
U equals y over x, and you plugged in the u.
You could do that too. Yeah. If you want, you can go to this one here if you want. You mean this one?
Right. And then
yeah.
it would just be,
you do your product rule there, right? You put the y, put it in here, and then you get the it just be u cubed plus u, right? Right. And you'll get to the same place. Let me just show you here. So, right, this is what u primed x plus u equals. Now over here, then they cancel out, right? You factor out the x cubes, and they cancel. So you just get u cubed plus u, like that. Which is, by the way, it'd be the same thing you get here if I subbed into this one, right? If I sub the y equals ux into here, right? It'd be the same thing because this would be u, this would be the u. And then over here, you do your derivative the same way. You would get this. Now, the only reason I showed you this here, you don't necessarily have to do these steps. You can leave these steps out. If you recognize this as homogeneous here right away, okay, then you don't have to do this manipulation here if you don't want to. Okay, but you can. You can if you want. If you want to do a manipulation here to write like this, okay, then sub in, you can do that. Okay. Or if you recognize it's homogeneous right away, you could just sub in here like that. So it's a matter of, if you want to skip that manipulation, you can there. That's the only thing. So, but okay. Anyway, end up with this here then. Anything there so far? Kind of made a mess of it. Anything there so far? Okay. Let's see. Okay. Oh, one other thing on this one too, on this original equation. Let's say also this is an initial value problem. We haven't had to use this yet, but let's say y of -1 is equal to -2. Back to our original one here. Okay, on our example, I forgot to write that down. Let's say it's like an initial value problem. We'll come to that later, but we'll add the condition on there. Okay, now anyway, here then, basically, you notice here then, these cancel out. This is like a separable differential equation now for u, right? So it's a separable. You'll get a separable when you do this. And actually, this is really nice because the u's actually cancel here. Okay, so you get like u prime x equals u cubed, like that. And so u prime x equals u cubed. Okay, so then you can separate it then. So basically, you get so I have like x du dx is equal to u cubed. So if you separate it out, you get u to the -3rd, right? So u to the -3rd there, and then du. Now this becomes 1 over x on this side then, dx. You see this here then? Okay, so that's just separating it out. Okay. Now, if these u's didn't cancel here, by the way, it could happen. It won't happen for us really here, but if these u's didn't cancel, it'd still be separable, but you'd have to do partial fractions. I don't remember from calculus 2, you have to do like a partial fraction thing. Okay. If there's still a u here, it'd still be separable, but you'd have to do a partial fraction or something then. But it's really nice that the u's cancel there. And so, but okay. Anyway, here then, now you get this. So then you do antiderivative. So that'd be what? U to the -2 over -2 equals then natural log absolute value of x plus c. Okay, so you get this here. Okay, and now we'll go about solving for u here then. So I multiply through by -2. So u to the -2nd is equal to -2 natural log absolute value of x. I'm just going to say, I know I keep going back and forth here. I'm just going to say plus c here now again. I'm going to lump the constants again. I think it's easier for now. Okay, so plus c there. Any questions, Nat? I just lumped the constant together there, Nat. Okay, and then, so what? Now this is like 1 over u squared. So, yeah, so 1 over u squared is equal to this. Or let's see, what I'm going to do there. Yeah, I'll just write this -2. We got this here. And so basically, when you turn this around, you get this here. Okay, so I have 1 over u squareds here then. Okay, and so that means u squared is equal to 1 over this. This is u squared here then. So then I take square root here. So then u is equal to what here then? That would be, now I can say here then plus or minus. I'll just do this for now. Plus or minus square root of then 1 over -2 natural log absolute value of x plus c, like that. Okay, so then that's the, okay, so we have that. Now I go back up here. So what was our thing then? So we call our substitution here, right? We call y is equal to, was it ux, like this? Right, so we got y is equal to, and then so that would be basically, I guess it would look like then plus or minus x square root of 1 over negative 2 natural log absolute value of x plus c. Okay, like this here. Okay, and another way we could write this here then, but this is y equals, if I clean it up a little bit, see if I can do this. I could break this into two radicals here, right? Radical numerator, radical denominator. So you can end up with this then here. I end up with this. So if I break it into radical numerator, radical denominator, and then you get this here. Okay, so anything there so far on that? Now notice here's a bunch of curves. There's a bunch of curves for the plus, a bunch of curves for the minus. Okay, we also had an initial condition here too on this. Okay, so initial condition, what do we have there for that? It was y of -1 equal -2. So now applied initial condition. Like that. Okay, so now what here? I guess the first question is now, do I want the positive or the negative here for this one? So how would that work? So which one do I want? So I'm trying to find the particular solution curve here. I have a bunch of them here, right? You got the pluses and the minuses. So which one would meet the condition here, do you think? Would I choose the plus one or the minus one? Yeah, I think because, right, when x, yeah, right. Because when x is -1, right, I put -1 here, okay? This is going to be positive down here. This is a positive number down here. We take the square root, right? This is going to be a positive here, okay? So you have negative over, this has to be positive down here, okay? Which means you want, so negative over positive makes negative, which is what we want. Actually, then, we want the plus one. We want the plus one here. Right? Because of the initial condition. So that would be then -1 over, yeah, so I'm choosing the plus one here to meet the condition. Okay, so actually, yeah, so I need to substitute in here then. Actually, let me do one more thing there. Before I apply the condition, I'm just going to make my, right, we're going to, so I'll say here for this one, we want this one here, y equals plus, and then this is the one we have to use here then, x over. Okay, so you have to choose the plus one here, right, for this. If I put -1 in here, I got to get -2 out. So yeah, I want the plus one there. So now if I plug in the condition, okay, plug in the condition here, so I get -2 equals, and that would be -1 over square root of -2 natural log absolute value of -1 plus c. So -2 equals, that'd be -1 over, that's going to be square root of c down here, right? Because this guy is 0, right? This would be 0 here. Okay, and so I guess you could square both, however you want to do it. You could square both sides now. So that would be like 4 equals, that'd be 1 over c you get here. So c is equal to 1/4, I think, by the time it's done there. Let's see. Checking that. Yeah, so c would be 1/4. Okay, so the solution here then, so finally, right, solution initial value problem would be y equals, that would be x over square root of -2 natural log absolute value of x plus c. Like that. So that would be the, or not plus c, what am I saying? Plus, we already found the c, 1/4, plus 1/4. Yeah, plus 1/4, right? So that'd be the answer here then to the initial value problem. Would be this. So that'd be the solution to it then. Okay. All right. So we'll do another one like that kind of. Any questions in that one? Going through it? Okay. So when you go through it, right, there's two possible signs in the U there when you go through it. So I may just carry those along. So now you get these here, and there's like, there's functions for the positive one, functions for the negative one. You got to pick the right one then, okay, for the initial value that we have there. So, all right, anything there? Let's see. Okay, let's try one more here. And I could put that in Desmos, or I could put it in GeoGebra. I guess I won't do it here, but I could put this in principle now. I could put this in GeoGebra here, get the slope field for it, okay? And then I'd have my initial condition, and then that'd be the solution curve, okay, through the point. So, but okay, so anything there on that? Going through it. Let's try another one here. Let's say we have dy dx equals xy plus x squared plus y squared over x squared. Okay, here we'll assume that x is greater than 0. Okay, so looking for solutions to this then. Okay, well, first thing here, this is actually, it's homogeneous. It isn't homogeneous because like we talked about here, right? If I look at the powers here, right, or look at the degree, this is degree 2, right? And this is degree 2, this term. This is degree 2. Denominator is degree 2. Okay, so.
Y is degree 2.
What's that?
Y is degree 2.
Well, yeah, the degree of it's 2 because there's x is 1 degree, the y is 1 degree. So we're talking about, you're not, yeah, it's not like an exponent where you can't add the exponents together, but just in terms of the degrees, this is degree 2. Okay, so yeah, basically, so this is going to be homogeneous here. So if you recognize it's homogeneous, now again, if you wanted to, like you mentioned there, you could divide it out, right? I could divide by, I guess by x squared everywhere. I think. Let's see, right? I can even break it apart. I guess if you break it apart separately here, you can give them as y over x's there if you want. But yeah, it's homogeneous, right? It's homogeneous, so you can use this approach. So what you do here, look for what then? Look for y equals ux, right, for solutions. So look for solutions like this. Okay, then you substitute in. So then you get what? That would be u prime x plus, using the product rule there, okay, plus u, like that. So that's using product rule over here. Okay. Got that. Now over on the right side then, you just sub in for the y there. So you get what? X times ux plus x squared plus, and then this is ux quantity squared over x squared, like this. So that's the subbing in the right side there. So wherever see the y, I'm putting the ux there instead. Okay, so we got u prime x plus u is equal to, and then now on the right side here, because it's homogeneous, you notice what happens. You see, if you do the exponent rules, you get x squared terms all across the top, right? And you get x squared in the bottom. You can factor out the x squared. It all cancels. The x squareds all cancel out. Okay, and you're left with what then? It would be, I guess, u plus 1 plus u squared. Okay, look at that, right?
First term,
Yeah.
x times u, the x is u, x squared.
Yeah. Yeah. Actually, let me write a bit more. I'm going to write another line here. U x squared plus plus exponent rules there. U squared x squared over x squared. Like that. Yeah. If you have x ux like this, Yeah, it's all multiplication, right? There's no distributing or anything here. It's all multiplication. So you just rearrange the factors. Yeah. Okay, so you can write like that. And then you notice here the x squareds, it all cancels out there on that. And we're assuming here x is greater than 0. X cannot be 0 here in this. So those all cancel out. So then you get what? You get u prime x plus u is equal to, then this becomes just u plus 1 plus u squared, like this. Okay. Now this is a separable equation now for, it's actually a separable equation for u here, but even better than that right now, these cancel out, those two terms there. Okay, so you get u prime x equals 1 plus u squared. Okay, it's separable here. If I write it like this for a minute, I get x du dx is equal to 1 plus u squared. Okay, get that? So if I separate it then, I get 1 over 1 plus u squared. Du is equal to 1 over x dx. Okay, now you integrate both sides. Okay, and this one here, it's been a long time, this one, this antiderivative here. Anybody know that offhand? The inverse. No. Stop. It's inverse tangent. It's actually inverse tangent. And if you need that, that'll be on a sheet somewhere. Okay, but it's inverse tangent. So you get inverse tangent of u here. Okay, equals, and then this is natural log absolute value of x. Okay, plus c, like that. Okay, so then if you solve for u here, take tangent both sides. So you get u equals tangent of natural log absolute value of x plus c. Okay, so then now recall that, I'll say here, recall what y equals ux. Okay, so the solution here would be what then? It's y equals basically x times tangent natural log absolute value of x and then plus c. Okay, so you end up with this here. So this would be answer here then. Now, well, yeah. So any questions on that one? One thing to mention here too, there was an assumption here that x was greater than 0. Okay, in this. So if you wanted to, you could also drop the absolute value here on the x. So you could just say ln x if you want. Okay, either one would be okay. I think the computer will take either one, but you could drop the absolute value there if you want on that, because there was an assumption x is greater than 0. Maybe I'll write that here. I'll just write this down. This is okay, or this is okay here. Okay, since we said earlier x is greater than 0. So either one of those would be okay there. All right, so that's how those go. Okay, the substitutions there. Anything on the homogeneous ones? We're done with that, and but that's the idea. That's the basic idea of those. There. Okay. Next thing then, we're going to start next section now. These are called exact equations. So section 2.5. Okay, so this will take some time now. Exact equations here. Okay. And by the way, I'm thinking the test next Thursday, I'll get more information about it. I'm thinking it's probably going to go through what we just did, the homogeneous. Yeah, what we just did a minute ago here. Okay, the homogeneous equations. I'm thinking that's probably what the test will go through next Thursday. So what we do now will not be on the test next Thursday. I have to break it somewhere, so it seems like a good place. So that's probably the way it'll end up. Okay, so the test next Thursday is going to be a bunch of those things where it says look for the solutions of the form, whatever, and you just plug them in and get your U and, kind of like that. So, but okay. Next kind is called exact equations here. And to start this here, actually, I need to do a little bit of a review. We've got to do a little bit of a review of partial derivatives, okay, from Calc 3. Okay, this is the one place in the course where you need a little bit of Calc 3 on it. Okay, so partial derivatives. Oh yeah. Oh, okay. So just a little bit of review here, partial derivatives. The quick partial derivatives review. Okay, from Calc 3. If you have a multifunction or multivariable function like this, okay, so like this here, so you have two independent variables, right, x and y, like this here. Okay, okay, let's say you want to find a partial derivative here. Okay, so for example, let's say you want to find a partial. It's a curly. Sometimes you write these curly d's like this. So this is the partial of f with respect to x. Okay. Another way to write this too is f subscript x, like that. It's another notation for it. Okay. In this case here, okay, how would this go then? So you take the partial with respect to x, 2xy. Basically, let me just talk through it just in case anybody's not sure of this. You treat the y like a constant, right? If you take the partial with respect to x, you treat the y like as a constant number. Okay, pretend the y is a constant there. Okay, so if you take your respect to x then, so how does this go then? Basically have this constant times x squared, right? So what that'd be and then take your respect to x, that'd be 2x. So you get 2xy. Okay, plus, now over here, how would this go then? Again, you treat the y cubed like it's a constant there. So you take your respect, if you take your respect to x, then you would do what? Say again. No, you're taking your respect to x.
Oh, so you do the first, then you do the second.
You just leave y to the third.
Can somebody tell me? Yeah, what would it be? Can somebody just tell me what it's? 7y to the third. Yeah. Okay. In other words, you treat the 7y cubed like a constant there. Okay, and that's just going to be a 7y cubed. That's it there. Okay, that's the partial with respect to x.
No, I had said 7y squared, but that's what I read.
Oh, okay. Okay. That's okay. Okay. Yeah, but you're right. Yeah, so that would be it there. So you just treat the it's not really too hard once you get used to it doing those. But you just treat the y like a constant number, and then so you end up with that. Okay. Now, for example, here, what about say partial of f with respect to y? Right. So don't say the answer. Maybe just take a minute and try it. Try it yourself. Just make sure we're good on this. So you take the partial with respect to y. Now you treat the x like a constant. Okay, so what would that be then?
Would it be x squared times 1 plus 21xy?
No, well, hold on. Okay, you treat the x like a constant, right? So x is a constant. Okay, so this is like a number here. So it's basically like a number times. Think of it like this. It's like a number times y, right? Plus and then 7y cubed, right? So if you had a number times y there, okay, so it'd just be the number, whatever that number is, right? So it's 2x, 2x plus, and then you just take the derivative with respect to y, 21y squared. Oh, I'm sorry, I dropped off. Oh, my bad. I'm sorry. I was looking. Yeah, okay. I understand. I was looking at this one instead. If I look up here. Okay.
Yeah, I had said that.
Okay, I believe you. So what would it be? What would we say then?
X squared times 1 plus xy squared.
Well, wait. Back up here. I gotta catch up here now. So that is what x. I should write them all vertically like this. That would be x squared. I agree with the first one. And then this one here would be what, 21?
21 XY.
Yeah. Plus 21xy squared, like that. Yeah, that's it there. Okay, good. Anything on that one? Let me try another one here. Let's say f of xy equal. Oh, actually, too, another thing I want to do here. You can also take second derivatives here as well. So, for example, if I want to find, say, this here now, so the derivative, the partial respect to y of df dx, like this. Okay. In other words, I want to take a second derivative here. Okay, say respect to y. Okay, the way you write this, the other notation, then that is f of, and it goes in this order here, yx, the way you write it there. Okay, and what that says is now here, you take, can I take the right order? Wait a minute. No, it's backwards. This should be xy here. This is xy. Like this, you write like this here. Okay, so this says you take the partial respect to x, okay, and then after that you take the partial respect to y, like this. Okay, so this notation here, if you're taking the partial respect to y of this one, you can also write like this. So you find partial respect to x and then take your respect to y. Okay, so what would that be here then? That's what I'm trying to say. What would this be? So I take the partial respect to x, which is this, and then take the partial respect to y. So what would that be here then? Yeah, I take the partial with respect to y now. So that'd be 2x plus 21y squared. Like that. Now, if I do the other order, if I, let's say I take the partial respect to x of df dy, like this, the other order, that's written like this then. Partial respect to y, then respect to x. Okay, and then now this says you take the partial respect to y, and then once you have that, then you take the partial respect to x. Okay, so how would that settle out here then? Well, so I'm taking a partial of this now with respect to x. Yeah, so 21y squared, right? So if I take a partial with respect to x of this, I get 2x plus 21y squared. Yeah. Like that. It turns out here, the mixed partials, like the second derivatives here, like the fxy, fyx, they'll always be the same. They'll come out to be the same all the time. Okay, so I'll just say here, these are always going to be the same. Okay, so anything there on that? I'm going to do another example. Slop through another example here. Let's say we have f of xy equals sine xy plus cosine x. Okay, let's see if we want to find this. F sub x, partial respect to x. Maybe try it yourself for a minute, and then you can correct me when I do it wrong up here. So try it yourself and then see. So partial respect to x. Remember, treat the y like a constant, right? And here you got to use a chain rule a little bit on that too. So. Right, so if you take derivative with respect to x here, that would be well, you get cosine of xy from the chain rule you got to do, and then multiply it by the derivative of this one here with respect to x. So it should be like this here then, cosine xy times y. Right, and then how about the next one then? Minus sine x, right? So minus sine x. So that's that one. Okay. Maybe I'll write the other one over here. How about now let's do the partial with respect to y. Try to keep it out of the way here. So do the same thing now, but find the partial with respect to y. Right, so this one here, how would it go? Be cosine xy times what here then? Times x, because that treating x like the constant multiplier here. And then anything else on it? Plus 0. Yeah, because this is a constant. Right, so this is constant here, because you treat x like a constant. So that just drops off. Okay. You can say plus 0 if you want, but that's it there. Okay. I'll write the plus 0 just for emphasis there, I guess. So, but anyway, that would drop off. So anything on that one? Okay. One more example here. Just for the practice here. Let's say f sub x, so partial with respect to x. So go through and try it yourself here. Okay, so partial with respect to x here. What would be the first term?
18x squared.
Right, 18x squared y. 18x squared y. That'd be that one. Minus some partial with respect to x here. You got to use the chain rule. So minus now derivative of e to the something. It's e to the something because e has its own derivative, and then multiply by the derivative of this up here with respect to x. So times what? Y squared. Yeah, because if you're taking the derivative respect, you treat the y squared like a constant, right? So you're taking derivative respect to x there. So it's this y squared you would have. Right, so that'd be that one. Any questions there on that? Again, the y squared, just think of it as like a number. So that number would just, that'd be your, that's the number that would come down here then. So, okay. Now, okay, let's say f sub y. Let me try this one here. Okay, so what would be the first term there? Yep, 6x cubed. Yeah, I got to work my way through this next one. Next one here then. So take your derivative here. So it's you got the e there. So it's going to be this again here from the chain rule. E has its own derivative. Now I got to multiply by the derivative. Well, multiply by the derivative of this now with respect to y is 2xy. Okay. Yeah, right. Because you treat the x like a constant, and derivative of y squared is 2y. So it's 2xy. Yeah, like that. So. Okay, so that'd be that one. Are any questions in that? So I think there's some of the homework where you do partial derivatives, so you'll get the chance to brush up on the homework some. You know, where you got to do those, but you might just brush up on those a little bit maybe if you need to. But okay, anything on that? The partial derivatives there. Okay, let's see how am I doing here. maybe I'll just do one more partial derivative to show you, and now I'll move on. Let's just say, I guess like this, just making something up. So maybe f sub x, try this for a minute here. How about the first term?
15x
Yeah, 15x to the fourth, y to the fourth, right? Because you treat the y like a constant. So yeah, 15x to the fourth, y to the fourth, plus, and then over here, that'd be 7 cosine x. Okay, how about partial, well, I'm going to mess myself up. Partial respect to y. Yeah, 12x to the fifth, y cubed plus 0. Yeah, right. So 12x to the fifth, y cubed. Then this would drop over here. So it'd be like that. Okay. Anything there? And I'll just show you one more time here. If I take the partial of this now, say with respect to y, right? So I take this one, take partial with respect to y of this now. What do I get here? If I take the partial with respect to y, that would be what, 60 x to the fourth y cubed, I think. And this would drop over here, right? That would drop. And then on this one, if I take the partial of this now with respect to x, so fyx, okay, this is what, 60x to the fourth y cubed. Again, just the observation, these match, right? The second derivatives match. Can we do that? The mixed partials there. Okay. Anyway, anything on that? Partial derivatives? Let's see. Okay. Now, another thing then from Calc 3. This will kind of lead into the exact differential equations. Just one result from Calc 3. And I'll just write this down here. We'll jump right into exact differential equations here then. But if you have f of xy equals c, like this, then it turns out you can write this here. Right like this here. So if f of xy is equal to c, then it turns out, and this is like an ordinary derivative here. I'm sorry, got dy dx, like this. Okay. Just real quick from Calc 3, I'm not going to spend much time on this because it's not really necessary to do next part, as long as you have this here. But if you might remember from those, if you had Calc 3 before, there was a formula for implicit differentiation. There's like a little shortcut formula. How'd it go? It was like a negative, and then I think it's backwards here. I don't know if you guys remember some Calc 3. If you had a function, you trying to do implicit differentiation, right? If you had a function like this, right? If you had f of xy equals c, right? If you had this here, and then there's a trick formula, for not really a trick. We went through it, okay. But along the way there, when we come up with this formula, this was like an intermediate result right before it here, okay. You could take this here. You can take this and write it like this if you move things around a bit, okay. Did I get that backwards? Wait a minute. Yes. Thank you. Yeah. Because I was going to say it wasn't going to work, but right. If you take this here, thank you. If you take this and write it around, you could. It's like this. You could turn it like this then, or if you multiply this over and do some stuff there. But anyway, this is the key thing right here, right? So in other words, So you don't have that part over there. But for example here then, say I have this here. If x squared plus y cubed x is equal to c, for example, okay, so that's like my f of x equals, say, c here. Okay, then from that, if I have this, then this follows from it here. Okay, I could say if I take the partial of this right here with respect to x, right, that would be what? That would be 2x plus y cubed. Is that right? I'm just writing this thing down here now. Plus, well, I don't need a parenthesis. Plus, now partial with respect to y here is, what's that? That would drop off there. That would be 3y squared x, or 3xy squared dy dx is equal to 0. Right, just as an example there, just by using this this thing here, right? Or in other words, now we're going to look at this backwards. In other words, if this is your differential equation, if you're given a differential equation like this, okay, this is the solution up here. Okay, so we're going to look at this we're actually going to do the backwards problem here, right? So in other words, okay, basically, so I'll just say we have found an implicit solution, right, to this ODE. Okay, I was kind of okay. So basically, what we're going to try to do now, we're going to try to take. So if we're given a differential equation here, we're going to try to run this backwards, okay, and get the solution, okay, like this then, okay. So really, what it amounts to here. So we'll kind of work on that. So that's the goal here. Okay, what we're going to try to do. Okay, so now a little bit of stuff here then with this. A few sentences with this. I got to write a little bit here now. Okay, so an ODE, or a differential equation. So this is where actually I'm going to start the part of exact equations now. Of the form let's say mxy like this plus n x comma y dy dx equals 0. Basically, that's like what we have here, right? There's some function of x and y here, okay, and some other function of x and y here. So equation of this form right here, we have some function of x and y, some other function of x and y equals 0, okay? Or another way to write this too, another more common way to write this when you do these equations, you could take the dx here, and if you multiply through by dx, there's actually a way to kind of flatten this out and write it too. Another way to write that equation is like this. It's the same thing as this. It's this right here. It's another way to write notationally, right? You can write like this here. Basically, it's multiplying through by the dx, kind of flatten it out. Okay, so if you have an ODE of the form like this, or you can write like this, okay, equals 0, it's called exact. It's called exact if, bless you, if, okay, the m is equal to f sub x, like the partial with respect to x here. It's a big if here, but if m happens to be equal to this, and n is equal to the partial with respect to y, okay, for some f of xy. Okay, so if this happens to be a partial derivative with respect to x of something, and this has to be a partial derivative of y with respect to, or partial derivative of y with respect to y of something, okay, then the equation is called exact. Okay, and then also then the solution, I'll say here solution is then, I'll say here implicit solution Let me say it this way. Plus the solution is then going to be this, f of x, y equals c. So this is kind of like the backwards statement of it here, right? So if this has to be, partial of something, and partial respect to y of something, okay, then the solution is going to be this here. Okay, so it's kind of running that statement backwards from up there. And so, okay, so anything there so far?
Could you actually go back and explain?
Yeah.
Oh, just a little bit. It's sort of-
Or this example right here?
Yeah.
Okay, we're taking this, okay, if you accept this here, let's just take this at face value. Take this one here, it's a Calc 3 result. If you take that, and if you take an example of applying, I made up an example here. So for example, I just invented an f of x, y. I just invented this here. Okay, so if I have this, say just like this here, okay, then according to the statement, right, I could write this. Okay, so this is the f of x, y here. So if I take the partial respect to x, that's this.
I guess I'm confused is what's the plus sign in between them? Like how did?
Oh, that plus sign, that's from
my
this.
God.
That's back from this. Wait, the plus sign between what and what?
Okay, so if you take the partial fraction with respect to x,
Okay,
I would get, the 2x plus
y cubed. Yeah,
And if
that's
you plug in
this.
yes, and if you plug that into that, it's going to be that plus the
Right.
partial.
Right. Plus that's this plus here. Okay, and then now if I take the partial respect to y of this, okay, that is this. Okay, so the partial respect to y of this thing right here, that's this, and then the dy dx is this, and it equals 0. Right. Right. So basically, if this, then this. Now we're trying to do it backwards. If this, we're trying to say, well, okay, we're trying to say here, okay, we have this differential equation. Okay, so this must be a solution of it. This would be a solution of it here then. Okay, we're going to, so yeah, in other words, this, right, the solution of this is this up here. So, okay, so, but that's the idea. We're going to try to do that backwards. So, let's see. Right. Now, one thing we need here then, okay, we need to know whether it's exact or not. So there's actually a test for it, a test for exactness. Okay, and we'll try to get through maybe one problem here, and then that'll be about it. But a test for exactness. Okay, I remember we said that the second partial derivatives were equal to each other, the mixed seconds. Okay, so one test for exactness here is this: is m sub y equal to n sub x? That's a test for exactness here. Okay, so if this is true here, okay, then it turns out the equation will be exact. Okay, so this basically saying the mixed second partials are going to be the same. Okay, let's try out an example. We'll just try it out an example here. Okay, we'll just run through one here. So say check if exact and solve. I don't know if we'll get through a tonight or not, but check if exact and solve. So let's see what this differential equation here. 2x. Oh, this is actually the one we just did. 2x plus y cubed plus 3y squared x dy dx equals 0. So we're kind of trying to do this the other way. So suppose we're given this equation now. Okay, we're trying to find a solution here then. Okay. So we got this here. Okay. Now, first thing here, identify the m. This is the m over here. Right? That is the m. And this is going to be the n. Okay. So, well, actually, I'm sorry. Let me back up just a bit. I want to write it one other way because the way they always write it. So this is your differential equation here. That's what we started with. I'm going to write it in the other form. I'm going to multiply the dx through it. So kind of flatten it out. I'm going to write like this. Okay. So I'm kind of, I'll put this in a parenthesis here, maybe like that. So what I did there, I just flattened it out and did a dx like that, okay? Now this is the m, and this is the n right here. Okay, we're trying to figure out, is this like the partial with respect to x for something? Is this the partial with respect to y for something? But to see if it's exact or not, what you do here, you find m sub y. Let's find m sub y here. What is that? So partial with respect to y is partial with respect to y, 3y squared. The 2x will drop because it's constant.
That's why I was confused.
Okay, that'll drop off because it's a constant, right? So, oh, I see. You're trying when we were 2x went before.
Yeah, I was like,
Okay,
what
yeah.
the heck?
Okay, because you take the partial respect to y, that's 3y squared. Okay, so that's that one. Now, what's n? What's the partial of n with respect to x? It's going to be 3y squared again, right? Okay, and those are the same there, like that. Basically, that's saying the next that could be right. Those could be partial derivatives. This could be an f sub x. This could be an f sub y because the mixed seconds then are the same, right? The mixed second derivatives are the same here then. So there's a chance that that this is exact. Okay, we can do that. Okay. Actually, this is exact now. Okay, so this is exact. Okay, now you kind of back up here then, right? This is the m and this is the n. Okay, we got that. So what you do here then, this m now, okay, this is going to be f sub x. So this is going to be your f sub x here. Okay, the m. Right, so m is equal to f. So the m now, that's going to be f sub x. Apparently, this is the partial with respect to x of something. So f sub x equals 2x plus y cubed, like this. Okay, and we're trying to recover now the f of x y here, right? So we got that. Because that's the m. Okay, now what you do here then, you want to take an antiderivative here of this, right? So we're trying to recover the f of x y here. So you take an antiderivative here. So we're going to like a function of x and y, like this. So our f of x y we're looking for. Okay, so basically m here is equal to f of x. Okay. Now f of x y then would be what? So imagine taking the antiderivative here, but pretend you took the partial with respect to x, right? So what would this be then here? If you took the antiderivative, treating y like a constant again, if you treat y like a constant, how would the antiderivative go here? X squared. And how about this term then? If you treat y like a constant, y cubed to x. Or yeah, I'll write like this, or you can say xy cubed. Right? Does that make sense there? Right? Because if I take the partial with respect to x here, what do I get? I get 2x plus y cubed. If I go the other way, take the partial. Right, like this. Now, here's the next part then. We're looking for f of x, y. Now, also here, you could have had some other function over here of y. I'm going to call it phi here. Okay, it's a Greek letter like this here. So it could have been from this. You could have this plus some function of y here, like this. Because what if I took the partial with respect to x here, right? I'd get 2x plus y cubed. What would happen to this if I take the partial with respect to x? This would drop, right? That would drop off. So right, when I'm going this way, if I'm going from here to here, I could have looked like this. Right? I could have some function of y over here, and it would have dropped off, right? Okay. Now, next thing you do here, this is a bit different, by the way, than we did last semester. I'm going to do it a little differently here. But now what you do, you take the derivative of this now with respect to y. Okay, so what would be the partial? Now, if this is our f of x, y here, what would the partial with respect to y look like of this? Right, this will drop, right? This will drop here, and that'd be 3xy squared, right? 3xy squared plus the derivative of this one over here with respect to y. So I'll call it phi prime y, like that. Okay, like this. Okay, now we also know here, right, this f sub y, that also has to be the n up here then, right? That f sub y has to be the n over here. Okay, so now on the left side here, I could write on the left side, I can write this then, 3y squared x equals 3xy squared plus phi prime y, like this. Okay, that's just, again, there, right? I'm just making this identification here. Okay, that's going to be our f sub y. It's this now. Okay, and these actually now drop off on both sides, right? So basically, you get that phi prime of y is equal to 0. Okay, because these drop off on both sides. They're the same thing. They're written differently, but because subtracted away. Okay, so those drop there. Now I can do antiderivative here. So that means phi of y is equal to what? If you take antiderivative of this with respect to y, that'd just be a constant. Since we're a constant here. I'll go and call it k, actually, here, some constant k. Okay, so now we found, right? So now we found an f of xy here, right? So I could say here, so we got what? F of xy is equal to x squared plus y cubed x plus some constant k here, like that. Okay, and I know that if I take the partial of this with respect to x, right, I'll get if I take the partial with respect to x, I get this one here. If I take the partial of this with respect to y, I get this one here. Okay. And so now, basically, then, if you set this equal to c, remember that statement earlier then, so solution is, right, you have x squared plus y squared, or sorry, plus y cubed x plus k is equal to c, like this. Because remember that thing earlier, from way back up earlier here, from this little thing here, right, using this guy here. Okay, so the solution here then is going to be this right here. Okay. But really, you don't need this k and the c here. I can move the k over and lump it in with the c. So you get x squared plus y cubed x equals c. Okay, so that's the solution to the differential equation. Okay, would be this one here. And by the way, whenever you do this part right here, you do this antiderivative, you could just put it, you could let the k be 0 here on this one. If you just get a constant here, you can let that k be 0, because you could put a plus k here, but it just absorbs over here anyway into this. So you could just say that's 0 if you like. So so that k, you can leave that as a 0 there if you want me to do that. But anyway, this would be it here. Then that's the solution to the differential equation then here then. Okay, so that's the answer there. So anything on that? Looking at it real quick. Now just jumping back real quick then, right? If I did back from Calc 3, if I did the implicit differentiation thing, to find a derivative of this, to find dy dx here, right? I do that trick thing or whatever from Calc 3, okay? And then if I move it around, right, I would end up with this here, okay? Which is our differential equation we're trying to solve. Okay, so it is true then. If you went through and did the derivative, if you find dy dx for this and move it around, you would get the differential equation we started with there. Okay, so anything on that there? I'll just make a note there real quick of that. Just kind of know about checking that there, right? If right, you can find dy dx here by this, right? Dy dx is equal to negative, and then it was f sub x and f sub y. Okay, and then if you did that, okay, move it around, move the equation around then, okay, and then you would get the original diffeq that we were trying to solve in the first place there, right? So anyway, that's the process going through. We got through it one time there. So I guess we're gonna have to leave it there, because on Thursday we'll do review. No. Test is next Thursday. So we'll do more of this on Thursday this week. Okay, we'll do more examples like this. Okay, hopefully they'll get easier because we've been through it once. And then next Tuesday, we'll do review, and then we'll do tests next Thursday. So, okay, any questions there? So, but we'll pick on this again. We'll pick up on this again next time here. Get through some more examples.